Delighted to welcome you all to the next session of our lecture series. We have Dr. Noel Jacob with us to provide us with new perspectives and insights into biocomposite based membrane technologies. Before that, let me take a moment to introduce our speaker. Dr. Noel Jacob Kalikal is an assistant professor in the Department of Chemical Engineering at NIT Calicut. He holds both his postgraduate degree in chemical engineering and PhD in technology from AC Tech Anna University, Chennai. He leads the membrane separation group dedicated to developing nano-enabled polymeric membranes for diverse applications. His impressive achievements include the Young Engineer Award 2022 from the Indian National Academy of Engineering, the Young Scientist Award 2022 from the Kerala State Council for Science, Technology and Environment, and the Young Engineer Award from the Institution of Engineers, India. Additionally, he serves as a member of the Bureau of Indian Standards Sectional Committee for Drinking Water Quality Standards. His research interests span membrane-based technologies, water treatment, fuel cells, and carbon materials. His group is actively working on government-funded projects focusing on the development of novel forward osmosis membranes and super hydrophobic membranes for the membrane distillation, aiming to recover and reuse wastewater and seawater. So let's welcome Dr. Noel Jacob Kalikal for the lecture on spectroscopic characterization of biocomposite membranes, development and applications.
Yes. Good morning. So I'm audible, right? Yes. Okay. So the talk for the next 1 hour is going to be on biocompatible polymeric membranes for particularly for hemodialysis application. So we're going to look into what is hemodialysis and what membranes exist today in the market for hemodialysis, as well as some of the work that we have done on developing new membranes for hemodialysis and obviously which have to be biocompatible. So globally, there are 3 million cases reported of end-stage renal disease, which is the failure of the kidney to do its function. And when it does, then often it is irreversible and the patient has to be on one of these renal replacement therapies like hemodialysis, peritoneal dialysis, hemofiltration, or finally the best option would be a kidney transplant. But since that is not very viable, hemodialysis is the most sought after renal replacement therapy. So what the hemodialysis does is exactly how a kidney would function. It would remove the accumulated uremic toxins, ions and water from the blood, and the insufficient ions what is required by the body would be replenished during the process. So hemodialysis is the largest market share per year. Can you change the, I think you have to change the back. Yeah. So hemodialysis is the single largest market for membranes with current excess of 15 to 10 power 6 meters cube membrane per year using membrane. So in India, it's particularly challenging because the end-stage renal disease affects relatively younger people compared to the western part of the world because of both diabetes and hypertension coexisting. And these contribute to around 63% of the cases of the end-stage renal disease. So if you look at the history of the artificial kidneys, as early as 1943, they have started using cellophane materials. So it's a cellophane wrapped tube. And this is a 2-meter horizontal drum which acted as a semi-permeable membrane. And a semi-permeable meaning it could allow the urea and creatinine or the uremic toxins to leave, whereas it retains blood components like blood cells. Yes. Okay. So this is the earliest application of the artificial kidney. So in now we have membranes that do the work. We have a range of membrane separations where membranes can be used to effect separations, and the range of filtration that we are looking for in hemodialysis lies in the ultrafiltration region. So again, so the filtration could include microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. If the pore size are larger than the microfiltration, it is conventional filtration, and all the others are membrane based. And in particular, we are looking at ultrafiltration membranes where you could effectively allow the passage of uremic salts but retains proteins, fibrinogens, etc. from blood. Yes. Okay. So this is the commercial Fresenius dialyzer membrane that is there, and this is a schematic of the hemodialysis process. The blood is taken out from the body and it's done extracorporeally, meaning it is out of the blood and it is filtered and it is sent back. So during the filtration process is where the membrane lies, and the membrane is able to remove water, it can remove uremic toxins, and it can remove any other unwanted ions, but it retains all blood components, proteins, etc., and it is sent back to the body. So in hemodialysis, the membrane acts as a thin selective barrier between the blood side and the dialysate side. So they are made to flow countercurrent. Dialysate would be just a buffered saline solution which contains ions which required by a particular patient, and blood is the what comes out from a human body. So both of these are made to pass across a membrane, whereas you have low molecular weight compounds can be removed. And uremic toxins are of three types. You have low molecular weight compounds which are less than 50 Dalton, that is urea, creatinine, which are the majority. Then you have some protein bound and lipid soluble compounds that cannot be removed by hemodialysis. And you have middle molecular weight compounds which are greater than 500 Dalton, which should also be removed by hemodialysis or hemodiafiltration, where the larger molecules also can be removed. So the membranes are, so the initial membranes were used for all cellulose, regenerated cellulose or cellulose acetate membranes, which have been used for a long period of time before they were finally given up. There are certain disadvantages of using cellulose which could be overcome when we add synthetic polymers. So synthetic polymers like polyacrylonitrile, PMMA, polysulfone, polyether sulfone, polyamide are all used in research, but polyether sulfone is the commercially used polymer for making hemodialysis membrane, and Fresenius owns the largest market share of membranes. So there are a lot of current researches to modify the membrane process, and one of that what we'd be looking at is composite membranes by introducing nanomaterials into polymers such that we can improve the biocompatibility of the membrane. Yes, so the membranes used for hemodialysis are classified as low flux, mid. Can you go back? Are classified as low flux, middle flux, high flux, or very high flux. So the flux would indicate the how much water is removed from the body, and that is per mmHg of transmembrane pressure per unit meter square of membrane. So if it is less than 10 10 liters per mmHg per hour per meter square of membrane, it is low. If it is greater than 20, it is high. So the disadvantages with using low flux dialyzers are the patient has to be on hemodialysis for a longer period of time. And if you use a higher flux membranes, the hemodialysis time. So the membranes that are prepared for hemodialysis are generally hollow fiber membranes, and this is how it's made into a membrane module finally when it has to be done, or this is the membrane cartridge as they call. So the polymer solution is spun using a bore fluid, and so one is an inert gas, two is the solution, polymeric solution, so it could be cellulose, it could be polyether sulfone, and through an orifice or through a spinneret it is made into form into a hollow fiber, and where 3 is your bore fluid. So basically you have a porous fiber. The porous fibers are then packed together into the form of something like a shell and tube heat exchanger, where it is packed packed. So it's packed on both ends. So you have a feed side and you have a shell side, or you have the lumen side and you have the shell side. So through the inner side of the fibers, you have the blood flowing, and in the outer module or in the outer shell, you have the dialysate solution flowing. So if you were to compare the different materials, so cellulose and modified cellulose were initially used for the membranes, and they were very good in sense that they had the modified cellulose had good biocompatibility. The sizes and the wall thickness were smaller, and they could retain. So 15,000 Dalton is what it could retain. I mean, greater than 15,000 Dalton, it could retain the solutes, whereas any uremic salts that are less than 15,000 could be cleared by the membrane. However, it could not capture endotoxins. So endotoxins comes in from the dialysate side to the blood side, and they had good biocompatibility, but they had high complement activation or moderate to high complement activation. So complement activation is something that is undesirable, that can cause death, and they are highly adsorptive membranes. So these are some of the features due to which the cellulose or the modified cellulose should have, I mean, are modified, or it has been changed from cellulose or modified to polyether sulfone. You have better performances, but the part is you have the compatibility increases, complement activation is low, and you have highly adsorptive membranes. Again, adsorption is not something that we want in our membranes, because if the blood cells are adsorbed on the membranes, it could lead to a cascade of undesirable effects like complement activation, or I mean, it can trigger a cascade of effects, could lead to death. So this is the SEM images of the cross section of these membranes. So if you can see that these have a diameter of 150 micrometer, and the wall thickness could be as low as 10 micrometer when cellulose membranes were used. When polyether sulfone membranes were used, it could be diameter was around 200 micrometer, and the and the wall thickness were higher, around 40 micrometers. And if you could see so membranes generally made in this method are asymmetric. Asymmetric membranes, on the blood side, you have the pores are smaller, and so it retains the solutes and it holds back the solutes, where on the dialysate side, the support layer, or the side facing the dialysate, the pores are larger, but it does not allow the diffusion back into the blood side. There are different physical and chemical properties that are required for the membrane to be used in hemodialysis. One is how hydrophilic or how hydrophobic a material is. So you would generally want materials that are hydrophilic in order for them to have better compatibility with blood. So there are many ways by which it is adsorbed, I mean, which it is achieved. One is by mixing with copolymers, one is by using nanomaterials which all impart hydrophilic properties to the membrane, and electric charges. So depending, the different charges can impart different properties to the membrane. So if the membrane has different charges, it can it can specifically reject the endotoxins that could come in from the dialysate side. So the functions of interest for a hemodialysis membrane are the solute transport, water transport, and blood compatibility. So solute transport being the uremic toxins from the blood have to be removed. Excess water stored in the body has to be removed. And more than these two, the material has to be biocompatible because it comes in contact with blood. So most of the solutes are driven out by diffusion, because we are not able to apply a pressure, because what happens is the blood cells could get sheared. So membrane thickness is the limiting factor when you have diffusion happening, because the diffusion of the solutes is, the rate of diffusion is indirectly proportional to the square of the distance, or the distance itself. So, and as the sizes increases, it increases exponentially. So hydrophobic membranes also adsorb protein layer that can reduce the in vitro clearance. So if your membranes are highly hydrophobic, they absorb the proteins from the blood. Again, that makes them poor to, it makes it poorer for solutes to transport because it adds an additional resistance. Coming to the water transport, okay, so these are the sizes, typical sizes. So urea is a solute of size of 60 Dalton, creatinine is something of 112 Dalton, and beta 12 microglobulin is around 11,800 Dalton. So these are the different molecules that exist in blood. So ranging from sodium, phosphorus, potassium are the smallest, but what we want to remove are uremic toxins. Urea is 60, creatinine is 113, and then we would want to remove beta 2 microglobulin, which is around 11,800. And your smallest protein that is present in blood is albumin, which is around 57,000 Dalton or 57 kilodalton. So these are the different molecules that are present in blood, and some of these have to be removed. For example, if sodium and potassium would automatically be removed, in order to not have the diffusion of sodium and potassium, the saline or the phosphate buffered saline that is used in the dialysate side has similar concentrations. So they have similar concentrations of sodium and phosphorus and potassium, so that the diffusion is prevented. Second is the water filtration. So like we talked about low flux and high flux. So low flux is the ultrafiltration coefficient is less than 10 ml per mmHg per meter square membrane, and high flux if it is greater than 20 ml per hour per mmHg per meter square of membrane. If you have lower flux or lower performance or lower flux, the patient has to be on dialysis for longer time compared to when you have a high flux membrane where the entire dialysis time reduces. And biocompatibility. So biocompatibility is, since it comes in contact with blood, it should not leach out anything into the blood, and it should not cause any adverse effects into the human body. So any inflammatory, any immune responses should be avoided, and more than that, the blood should not clot as it is flowing through the hemodialysis. Heparin is always added. Heparin is the well-known anticoagulant, and it is always added. But in spite of that, there are instances of clotting happening within the membrane pores. So in order for that, the membrane that we make has to be biocompatible as well. Biocompatibility depends on a lot of parameters like protein structure, hydrophilicity of the membrane, surface charge of the membrane, protein adsorption, but they are not exclusively related to the membrane. It can differ from patient to patient also. So, this is some of the work that I had done a while back. So, this is when we try to make similar biocompatible membranes. So, we have chosen a polyetheramide membrane polymer to make the membranes. So, it has a lot of advantages why we choose polyetheramide membranes. One of them being that since your operating temperature is quite high, it can be steam sterilized or UV sterilized as well, because all products that come in contact have to be sterilized before use. But we have some limitations, the main being they are hydrophobic and they foul the membrane. But they have been seen to have used for a lot of different applications like substrate for growing bone cells, artificial muscles, biocompatible actuators, etc. So what we have tried to do is we have tried to improve the performance or improve its biocompatibility and hydrophilicity by using different nanomaterials. So low dimensional carbon nanomaterials, what we have chosen, because carbon as such is quite inert and it doesn't cause any toxicity. There have been studies where graphene oxide has been used or injected into rats and they did not cause. And anyway, we do not want any of these nanomaterials leaching out from the membrane into the bloodstream as well. So we have done graphene oxide, carbon nanotubes, and functionalized graphene oxide, where we have coated the graphene oxide with heparin. The heparin was anchored to the graphene oxide using a bioglue or a bioadhesive, that is the dopamine, and carbon nanotubes. So carbon nanotubes have also been used for other applications. So we thought that they would be a good fit for hemodialysis membrane. So this is one of the work on graphene oxide nanocomposite incorporated polyether mixed matrix membranes for hemodialysis application. So we have prepared graphene oxide. So graphene oxide today it is well known and is widely used in a large number of applications. So we've used by the conventional chemical synthesis route. And once that was done, that these graphene oxide were characterized. So I am not going in detail into the characterizations because that is not the point here now. So they were extensively characterized and identified that the graphene oxide is formed. So graphene as such is carbon that has no functional groups, but we need it in its oxide form because it imparts, I mean it gives the OH, COH or epoxy oxygens that would increase the hydrophilic character of the membranes. So they are again evaluated by TEM, XRD, UV spectra where we could find the band gap and 2 theta, etc. So then these were used to prepare the polyethyramide membrane. So we use polyethyramide as the polymer. PVP, polyvinyl pyrrolidone is used as a plasticizing agent. So since we want our membranes to be flexible, we use polyvinyl pyrrolidone and we've used increasing concentration of graphene oxide. So the advantage of using nanocomposite membranes, one is that very low percentage of nanomaterials is enough to effect a very large change because these nanomaterials have a very large surface area and we've increased them. So, and they were casted as flat sheets using a semi-automatic casting unit and you can see these optical images of the membranes, and as the concentration of graphene oxide increases, the membranes become much darker. Again, so after that we want to confirm that it has been successfully incorporated. So again the membranes have been characterized by FTIR. So interestingly, when we added the graphene oxide, the surface charge has again become more negative. So at a pH of 7.2 or 7.4, which we ideally use for hemodialysis. So more negative surface charge would indicate that the negatively charged endotoxins could also be rejected by electrostatic force. And this is the cross-sectional morphology. We can see that there has been a denser top layer being formed as the concentration of graphene oxide increases. This is because during the phase inversion, so I am again not going into the details of the membrane preparation part, but during the process of phase inversion, the graphene oxide migrates to the top surface of the membranes and thereby making it thicker, dense top layers and a more porous sublayers. And the AFM images also, so there was changes in the membrane roughness when we used graphene oxide as well as the contact angle. So contact angle is a direct indicator of the hydrophilicity of a membrane. So if you have a water dropped on a surface, we measure how much it spreads. The more it spreads, the more affinity water has with the surface. So blood is again the major component on blood is water. And since it is more hydrophilic, the membranes in contact with blood would also not have, I mean, would be having least adverse effects compared to the more hydrophobic surfaces. So again, these are some of the formulas that were used to calculate all these parameters. So another important parameter is, so we spoke about clearance of low molecular weight solutes, but now albumin, which is the protein present in the blood, should not be released or should not pass through the membrane, because if that does, then that is another problem altogether. We want the low molecular weight toxins to move across the membrane or to be filtered out, but holding in the proteins or red blood cells, etc. And these membranes showed 97-95% retention of the bovine serum albumin, making it a potential candidate for hemodialysis. So the ultrafiltration run, so that is the ultrafiltration rate, that is ml per hour per meter square per unit mm of Hg or mercury. So we can see that on increasing the nanomaterials, the membrane fluxes had increased or the ultrafiltration rates had increased Again, this is what we were looking for. We want membranes with much higher ultrafiltration coefficients such that they become high flux membrane dialysis. So M3, M4 are above the 20 mark. So the 20 ml per hour per meter square per mmHg is the threshold for classifying it into low or high cutoff or high flux membranes. So these membranes achieve that part. So then it comes to the biocompatibility of the membrane. So biocompatibility often starts with saying if the proteins present in the blood start attaching to the surface. Once it starts attaching, it forms clots. It brings in the platelets, it forms a clot. It could lead to further complement activation and finally, like I said, like death. So in rare cases, it can even, patient could even die. So BSA stands for bovine serum albumin and FNG stands for fibrinogen. These are the most widely available proteins present in human blood. And you can see that as the graphene oxide concentration increased, the absorption of bovine serum albumin as well as fibrinogen were much lower. Again, this is again because it makes the surface more hydrophilic. Proteins attach to any surface by hydrophobic interactions. For those of you who have heard of this, so the more hydrophobic a site is, the hydrophobic interaction between any molecule. So proteins generally absorb by hydrophobic interactions, and that could be prevented if your surface became less hydrophobic. Platelets. So platelets starts when again blood is in contact. Like if you have a wound, you platelet starts forming and clotting happens. So we don't want clotting to happen when the blood is in contact with the membrane, because if clotting happens, blood flow stops and then the blood doesn't return back and the patient could eventually die. So platelet adhesion was low and the number of cells counted in 10 powers 4 cells are much lower. These are all different parameters that we use to calculate the biocompatibility of the material. TAT stands for thrombin, antithrombin, again an indicator of clotting. And APTT and PT are activated plastin, thromboplastin time and prothrombin time. So these two are indicators of clotting time. So ideally, blood, once it is out from, or a drop of blood would clot in some time. For those of you who have noticed. So when it clots, it becomes much more stickier or much more viscous before it finally hardens. So the clotting, an increase in clotting time is that which is desirable because it helps the blood to flow through the entire filter without clotting in between. So, but there is not very significant increase from around 37 seconds to just around 80 seconds. So there is not much significant increase, but again, we don't want it to decrease even if there is no significant increase. This C3, C5 are two complements. There are different pathways for complement activation, direct or indirect. Again, that I'm not going into that in detail of that. So, but we would like to see that the membranes M0 in both cases they activated these complements which are undesirable, but the modified membranes were lower than the control, which in a way was good because they make the membrane safer from complement activation. So finally, we had tested the membranes for the biocompatibility, and once we found that they were biocompatible, we have done a in vitro study for removing solutes. So the three solutes chosen were all from different size ranges. So you have urea. Urea is around 60 kilodalton. Vitamin B12 is around 1060 Dalton, not 60 kilodalton, 60 Dalton, very small. Vitamin B12 is 1000 and cytochrome C. Cytochrome C is not, I mean, it doesn't exist in the body, but it was used as a surrogate molecule. So surrogate meaning instead of lysozymes which have around 11,800 Dalton, instead of that, because cytochrome C has a color and it's around 12,000 Dalton and it can be easily visualized with any kind of spectroscopy. So that is why we used. So the permeation coefficient, obviously smaller molecules migrate faster. You have very high rates of permeation coefficient, but as the size increases, so exponential decrease in the permeation coefficients could be seen. So, and as expected, permeability of urea is greater than B12, greater than cytochrome C, which is in the order of its molecular weights. Another thing done was the cell compatibility. So this was done, I mean, so there are ideally no other cells except blood cells, no other cells come in contact with the membranes, but this was just done to understand whether cell adhesion takes place. So there is not much cell adhesion, and we don't want cell adhesion in fact, like, but whatever adhered did not die. So both of these were like positive results that would say that the cells have cytocompatibility, but it cannot be used as a platform for growing cells. So then we had moved to multi-wall carbon nanotubes. So from graphene oxide, again same family, only thing its structure is different. So when the structure is different, we found that it also plays a role in selectively permeating the solutes that we don't want, or the uremic toxins. So again, I am just going to skip through these characterizations. These were the HR-TEM images of these. Again, so, and this is how we made so we've made both flat sheet as well as hollow fiber membranes in this case. And you could see HF, the ones that have an HF notation stand for the hollow fibers, and the ones that are M0, M1, M2, M3 are all flat sheet. So we used polyether imide membranes again with the same plasticizer and different varying concentration of the functionalized multi-wall carbon nanotubes. So the carbon nanotubes again are inherently, they have only carbon, and unless they are oxidized, they don't have any functional groups. And once they are oxidized, they have any oxygen functional groups, OH or COOH. That again makes it hydrophilic and able to disperse into the polymer matrix. So I would just go to the biocompatibility part of this, where we've used human serum albumin. In the previous study we had used bovine, like, so the serum albumin, the source was from from a cow. But this is the actual human serum albumin, and gamma globulin and fibrinogen are all human proteins. So we wanted to see that is there any difference, because obviously from the source where we take the proteins, it does molecular weight slightly change, and we wanted to see. So we could see that the relative adsorption of proteins were lower than 25% as compared to the pristine membrane without any carbon nanotubes. So increasing the hydrophilicity did play a role in preventing attachment of proteins. Again, attachment of protein is something that we do not want. So platelets. So you can see that on the first one, you can see that once the platelets adsorb on the surface, it starts to form a network along with the fibrinogen. So what happens is it creates a mesh. So that is how an actual clotting happens when we have a wound and the bleeding stops. So that is a very positive thing, or that is what we require. But when we do the hemodialysis, we do not want the blood to clot on the membrane surface. So you can see that as the concentration increase, though there are now in this case there are few platelets that are adhered on the membrane, but they do not spread out, or they do not form the fibrin network. And at higher concentration, we are not able to see visually any platelets. So those are platelet adsorption as well as platelet activation. So this is adhesion, as well as now this is the clotting time. So again, clotting times, again small increase in clotting time, which is a positive trend, meaning we want our membranes to, we want membranes to be able to withstand clotting. Hemolysis. Hemolysis is if when the RBC comes in contact with a biomaterial, we want to see that if it denatures or if it ruptures the blood cells. So less than 5% is okay. That is well within the ASTM safety limits for biomaterials, and this was very low, like around 0.25, and this was comparable to the commercial dialyzer membranes that are available today in market. Again, we did live cell, dead cell culturing. Like I said, we do not actually want cells to adhere on the membrane surface, but we saw that there was small adhering on the membrane, but those cells did not die. And but again, this is just for the sake of evaluating whether a cell would die when it comes in contact with our membrane surface. And these are the hollow fiber membranes, the cross section of a single fiber. So this is a single fiber that has a dia of 220 micrometers and wall thickness from 45 to 55 micrometers. So you can see that how the membrane morphology or the cross-sectional morphology changes when we add carbon nanotubes. So here you have more porous membranes as compared to here, and larger pores. So when you have larger pores, it in effect it leads to faster ultrafiltration fluxes, or your flux water permeation through your membrane automatically increases. But if it's very large, then all the solutes or the blood itself crosses over, which we don't want. And another additional property to these membranes were it could have an adsorption of the toxins as well, because the carbon nanotubes acted as sites where it could particularly pick up creatinine. So the two levels of creatinine, so initial creatinine, which is normal level, that is around 1.2 milligram per deciliter, and we did a spiked one where it is 5.4 milligram per deciliter, and we saw that there was always an adsorption of the creatinine by the membranes. So the relative concentration drops, meaning some part of the creatinine was adsorbed on the membrane surface. And the maximum adsorption occurred within half an hour. So which is again good, because the entire hemodialysis run is around 3 to 4 hours for a normal patient. So within half an hour, if it adsorbs, then that is again a positive sign for the membrane. Ultrafiltration, so as the pore sizes increase, your ultrafiltration rate again increase. So again, these are measured in ml per meter square per hour per mm of Hg, and you add 98% retention of your bovine serum albumin. So that means you had good clearance of solutes, you have, I mean, good clearance of water, but your membranes could withhold essential proteins like bovine serum albumin. And so these are similar to what we have today in markets. And then we did the run. So here creatinine cytochrome C removal was evaluated in a, again, counter current mode. So you can see the modified membranes, or the membranes with the carbon nanotubes had higher removal of creatinine as well as cytochrome C. The removals are different because again creatinine is around 116 Dalton, and again cytochrome C is around 12,000 Dalton. So the removal is less. I mean, that is as expected. But if you increase the flow rates of the dialysate, again we saw a slight improvement in the performance. So that is also good, because this is within the operational parameters approved by WHO or the US government. So this is the last work where again now we have improved the clotting time of the membranes by introducing heparin, which was bio-anchored onto graphene oxide, and that was used to make these hollow fiber membranes. So this is something that we have patented. Okay, so you can see now these are the membranes. So it's very difficult to take a cross section of the membrane, because the membranes, the sizes, the dia are very small, so around 220 micrometers, and wall thickness are again 40 to 45 to 50 micrometers. Again, all these the same kind of biocompatibility assays we have done. And here the interesting thing is the clotting time. So previously there was no significant increase in clotting time, or it just doubles from 40 seconds to 80 seconds. Here you could see that the around 37 seconds, the clotting time has almost reached around 250 seconds. So again, this is heparin is a well-known anticoagulant, and it is used to prevent, during any surgery, it is used to prevent clotting. So when we had immobilized it on our membranes, we saw that the heparin was still active, and it can still impart its properties. So urea lysine. So in 3 hours we check the reduction of urea and lysine. So in within 3 hours you have greater than 90% removal of urea, and lysine removal of more than 60%. So this is what happens in a typical one single run of dialysis as well. And so we compared, so F60S is the commercial Fresenius membrane that is available to us. I mean, that now people use in the market, all hospitals use this. And this is what we had prepared. So the ultrafiltration coefficient was slightly higher. We were able to make only a 0.66 meter square membrane. So that is because we had limitations in making larger area. The blood flow ranges were similar. Wall thicknesses were slightly higher than the commercial one. The membrane material here was polysulfone that is used in Fresenius, and we have used polyethylamide plus the graphene oxide one, and the beta 2 microglobulin. Beta 2 microglobulin is the middle molecular weight solute, and we could remove it 63% within 2 hours. And these are the SEM images of the two, the R membrane as well as R membranes. And so we were in line with that. So after the lab trials, this had gone to an in vivo study where it was done using rabbits. And the first line of, for the first line of trials was successful, and now it has been moved to doing it on larger animals before it comes for clinical testing. So coming to the market scope, so there is a huge scope for the hemodialysis market. So there is a year-on-year growth, and you can see that hospitals, inpatient hospitals use hemodialysis, and because of that, there is a large increase, or there's a demand. This also means that there is an increase in patients suffering from the kidney failure or end-stage renal disease. So, but the market scope is increasing year on year. And I think so with that, I am going to wind up my topic. So today our focus has shifted from hemodialysis. So we work on desalination, gas separation, resource recovery, as well as concentration of compounds. So I would like to thank the Indian National Academy of Engineering, the Kerala State Council for Science, Technology and Environment, the Institution of Engineers India, for their support to the work or their recognition to our work. And we had some of our government funded projects. I would like to thank the MHRD Spark, the Startup Research Grant from the SERB, the DSC Technology Mission Division for Energy and Water Support, as well as the FIST grant to the Department of Chemical Engineering. We have some more projects that are sanctioned currently under the Water Technology Initiative of the DST, as well as from the Ministry of Earth Sciences. I would also like to thank NID Calicut as well as the Department of Chemical Engineering for the support, the faculty seed grant as well as the student support that we receive year on year. So with some of that, we have a lot of facilities that have been available to us in our department. We can make membranes, so you could make it electrospinning, you can make it casting. We have all kind of testing facilities, osmotic driven, temperature driven, pressure driven, reverse osmosis which goes up to 69 bar pressure, as well as a lot of membrane characterization we have in our common instrumentation facilities, and we have a lot of other testing facilities that are available. So I would like to thank some of these works. We have international collaborators at UTS, University of Arkansas, UMBC, as well as Khalifa University. And the students who are working in all these projects, I would like to thank them. And I would like to thank the organizers of the GYAN, Professor Unikrishnan and Dr. Raju, for the kind invitation to this lecture. And with that, thank you. I can take a few questions if there are any.
Thank you, sir, for your wonderful lecture. Now the session is open for questions. Questions?
Sir, in your slide number 50, some microscope you are shown in that live cell and dead cell, right? Yeah. That facility is available here?
No.
Okay. So here in the blood, this.
So this was done, okay, so this work that I have shown was that was part of my PhD work. So this was done at a medical college that had a clearance for doing animals as well as handling cells. So it was at the Sri Ramachandra Medical College. So that facility is not available here, yes.
So in that dialysis, this cell, dead cells and live cells shown red and green color, right?
Yeah.
So
that is by a stain.
Stain, okay. Dead cells means
Cells have died. So so how that is generally carried out is onto whatever is our support, we add a certain known amount of cells. So number of cells per volume. So it will be in a solution, like it will be in a buffer. So we know approximately how much volume of cells are there, and we add it to all our test samples. So we make it, so these have been incubated for 24 hours, 48 hours, 96 hours, depending on what is our test. And at the end of that, we do the staining. acridine orange, ethidium bromide staining is done. So selectively, if the cell died, that means if the cell wall has lysed, it would take up a particular dye, and if not, the cell wall would take up the other dye. So that's how we know that how many cells are alive and how many cells were dead.
And sir, you mentioned that this diffusion is the mechanism for
Yes,
this.
of transport, yes.
So how will select which the diffusion means it will absorb the all wanted and unwanted cells, right? Means
So
particles.
diffusion is across the membrane. So diffusion of the solutes are across the membrane. It is not onto the membrane. So we don't want anything, ideally we don't want anything attaching to the membrane, except in one of those cases where we tried to absorb creatinine. That was, we tried to do the absorption. But as such, we don't want anything to stick on the membrane. What happens is over time, if something sticks on the membrane, it creates an additional resistance. Okay, so diffusion is the mechanism, and smaller solutes migrate faster than larger solutes. Fick's law. Okay. Once we establish the Fick's law of diffusion, so you are saying that all solutes can migrate. Yes, absolutely. All cells will migrate. So if I were to go back, so you could see that sodium, potassium are much smaller than urea. So urea is around 60, sodium is around 23 Dalton. That is the size of the so in order to prevent sodium, potassium or phosphorus from migrating across the membrane, the dialysate would be an isomolar solution. That means it would have the same concentration as you would want it in the human, as you would want it in blood. So that prevents the diffusion because there is no concentration difference. The driving force for diffusion is always a concentration gradient. So when there is no concentration gradient, it doesn't diffuse. Second, larger solutes. So solutes larger than 12,000 or 15,000 Dalton should not diffuse because like proteins. So that is on our pore size. Though it wants to diffuse or though it tries to diffuse because of the concentration gradient, the pore sizes are too small for it to allow it to transport. Yes, does that
Thank
clear?
you. Yeah, thank you.
If there are any more questions, I will take. If not, loudly.
Patients who are taking medications, drugs, even though kidney acts as a filters, some of the drugs will be there in the blood. Hemodialysis will also be such kind of things. So will it?
No, it will remove those drugs. It again depends on the size. If the size is below the pore size of the membrane, it will remove them, and then the patient has to be given the medicine again. So there are medicines that are given that so they last longer and they give the effect, whatever is the particular drug. So if the pore size, if it is smaller than the pore size of the membrane, if the patient undergoes dialysis, it will be removed. So the after dialysis, immediately the patient has to be given that drug. Yeah.
For some medication and some cases, even if the patient skips one time medication, the drug which is already existing in the blood prevents some bad happening to the patient, right? So if hemodialysis happens, then the patient need to be immediately medicated.
Yes. Yes. So that they take the history before doing dialysis. They take the history. So any drug that is essential to the patient, it will be removed. So the patient has to be medicated, or it has to be given in higher doses such that even after hemodialysis, some percentage is retained in the body. Yes.
Also, that kidney functions all 24/7, but in hemodialysis, as you said, it was done.
Yes, 3 hours, 3 to 4 hours, and depending on the severity of kidney function loss, minimum is 2 or 3 times per week. And there are patients that undergo daily also. If it's 100% thing, so they daily have to undergo hemodialysis and they will be on a strict diet of low sodium, etc.
Sir, you mentioned about that leaching out process, no?
Leaching off.
Leaching out process. That for a system to be biocompatible,
Loudly.
for a system to be biocompatible, leaching out should not happen. That you mentioned in your slide, no?
Yeah, if whatever we use to modify the membrane, nothing from that should leach out into the blood.
Okay, then how you characterize that? method?
Leaching.
Yeah.
So that we will do a leaching study, right? So the same condition in which the blood is, we would prepare solution and we will leave it in that. So it can be at 37 degrees, at 7.4 pH, under a slight agitation. And we would do it for up to 90 days for us to understand if there is any leaching. Even if it's very low, it's very difficult, and carbon is very difficult to find out if very low concentration of carbon has leached out. So that we would do it even up to 90 days
Okay.
to ensure that there is no leaching.
It's time to start.
Sir, usually pharmacy drugs undergoes phase 1, phase 2 trial, such kind of thing.
Yeah,
For this hemodialysis also?
definitely. So
Oh,
this is just in, no, it's not over. These are just done in small animals. So next would be dogs or horses, because they inherently they get kidney failure. In rabbits and all, the kidney failure is induced to make the kidneys to fail. But these pedigree dogs or these hybrid horses, inherently they get kidney failure. So that would be the next step.
Next, I would like to invite Professor Allen to hand over a token of love to Dr. Noel.